All right, state Newton's first law of motion. I like to think of Newton's first law of motion sort of differently than the textbook definition. So as a student, you can kind of think about Newton's first law of motion says objects don't just accelerate on their own, right? They just go at constant velocity. Objects move at constant velocity. Now, one constant velocity that's kind of special is 0 meters per second, 0 miles per hour. That's constant velocity, right? A constant speed of 0. That means at rest. And so when you typically hear Newton's first law, it's like objects that are at rest tend to remain at rest. Objects that are in motion tend to remain in motion. But we can capture both of those ideas with objects move at constant velocity. And one constant velocity is 0 or rest, but it still is just, a constant velocity. Unless a resultant force or a net force or an unbalanced force, here in ACE physics, pre-ACE physics, let's get used to the language, the resultant force. We can see one of the learning objectives with chapter 1, we're trying to relate, sort of Newton's first law to all the learning objectives of non-accelerated motion. And one of those learning objectives is to use vector addition to add 2 or more vectors. And remember, we call the sum of 2 vectors the resultant, right? We add 2 vectors and we get the resultant. And force is a vector, right? And so when we sum all of the forces, there's a resultant force, okay? That's going to make an object change its motion from constant velocity, right? And it will accelerate. So what does it mean to move at constant velocity? It means we're not accelerating. So objects don't just accelerate on their own. A net force or a resultant force is required to make them accelerate. All right, so I will say, I'll kind of put that in my own words here. Objects, you could say maintain their current state of motion. I would say objects move. I wonder if that's going to also be recorded. Well, this is science class, and so we'll test. Objects move at constant velocity unless a resultant force acts. Right? A net force, a resultant force. And remember that this is also sort of capturing the idea that objects that are at rest remain at rest. That's just a unique constant velocity of 0. Right? So you could put that, you could spell that all out if you'd like to, but you kind of need this key idea. Objects just move at constant velocity. This is the law of inertia. So inertia is mass, and it's a tendency to resist change in motion. And so objects tend to resist any change in motion. If they're moving, they tend to keep on moving. If they're at rest, they tend to keep on at rest. And the thing that changes that is a resultant force. Easy come, easy go. All right, now we've got a block of weight 15 newtons, hangs by a wire from a remotely controlled aircraft as shown in figure 2.1. The aircraft is used to move the block only in a vertical direction. The force on the block due to air resistance is negligible. The variation with time t of the vertical velocity v of the block is shown in figure 2.2. The velocity is taken to be positive in the upward direction. Okay. And our first task is to determine for the block the displacement from time t equals 0 to time t equals 3 seconds. And we need to solve for both the magnitude of displacement and the direction. So remember that displacement is a vector. In fact, it's one of the things that we want to sort of revisit with this kinematics learning objectives, right? Define displacement, speed, and velocity. So here we're determining the displacement. I have to kind of picture this in my mind. I want to kind of like interpret this data. Like what's really happening here? And I kind of think about it as like somebody dropped this thing out of a window, like they're like, all right, the moment I drop it, let's turn it on. All right, but I'm just going to sort of drop this drone out of a window here, and it's got a string with a block on it. And so the thing is moving like downward pretty fast, right? Like this is a negative velocity, and they tell us that positive is up. So it's moving downward the fastest it's ever going to move, and then it's slowing down, slowing down, slowing down. Right? So it's like we turned on the propellers and this thing that's falling, probably because it has weight, right? So it's like its weight is just making it fall, but then you turn on the propellers and that's making it sort of slow down or decelerate, right? Until it reaches a speed of 0. And so what would that kind of look like? That would be a drone that's falling, but the propellers are moving sort of furiously, right? And eventually it just sort of slows down, and now it's not moving down anymore. It's at a speed of 0. But then what happens? It starts to move up, okay? And so right at 2 seconds, it sort of slowed down all the way to a stop, but then it just starts moving up again, right? The propellers sort of allow it to fly. And that's the way we have to kind of get used to interpreting this velocity time graph. And so that's actually, this is acceleration, right? Like the slope of this is the acceleration. The slope of a velocity time graph gives acceleration. The area underneath it gives the displacement. So that's kind of the way we need to think about solving this problem, is calculating the area here, like this triangle from the x-axis, the time axis here, that would give us the displacement that like it fell out of our window, right? It falls a pretty good distance. And in fact, by inspection, you can just kind of eyeball it that this area is bigger than this area. Like this is the area where it's moving upward, right? So it doesn't make up as much ground as it dropped, just by inspection. Just looking at that scaled graph, we can kind of see that the net displacement is going to be in what direction. Like in other words, we already know the direction of displacement. I'm pretty confident that it's down, right? Like it's covered more space down than it made up for it back over here up. And so the path to this solution is calculate the area of this triangle, calculate the area of this triangle, and subtract them. And I'm pretty sure that this is going to win, right? Just kind of looking at it, it doesn't seem like this is, made up as much ground as it dropped. All right, so let's kind of go through that working together here. And I suppose the other way to solve it would be with like an equation of motion, which, remember, these equations of motion come from a velocity time graph. So if you said, well, I just used like a displacement, I solved for displacement with an equation of motion, you could have done that, but I think you would have to do it twice, right? Because you do have to sort of solve for the down part and then sort of the up part. So I'm just going to kind of work with the graph here. All right. If we read the y-axis carefully, then each one of these divisions is 0.2, right? So it goes 6.2, 6.4, 6.6, 6.8. So this coordinate here is negative 6.8 meters per second. That's the initial velocity. Right, at time 0, it's going that fast, but then it slows down, right, to 0. And so at this point, it's at a stop. And so if we think about the area of this triangle, it's 1/2 length times width, or 1/2 base times height. And so let's call this the length, 1/2 negative 6.8 meters per second. I'm keeping the negative sign to remind me that like negative is down, and I'm going to have to sort of add these two, but like add the negative, right? So I'm just going to keep the negative sign in there so I don't sort of forget that. And then the width would be 2 seconds, right? It's just sort of this part of the triangle there. So negative 6.8 meters per second times 2 seconds. The seconds cancels. We're left in meters of displacement, which is kind of what we want to calculate. So remember, the units are a big clue that you're on the right track with that. Everybody with a calculator knows that 0.5 times negative 6.8 times 2 is negative 6.8 meters. And even people without a calculator knew that, because they were like, well, half of 2 is 1, and 1 times this is just this. So why'd you get your calculator out? Just because I want to sort of be really confident in my answer, okay? Back off, all right? I like using my calculator. It's just a joke, class, okay? Lighten up. Oh no, let's be consistent. Length times width. All right, now we need the area of this one here. It's good that students sort of know my sense of humor by this time of the year, because when I use those jokes at the beginning, they're like, whoa, what's this problem? All right, what's this one over here? It looks like 3.4, right? If you got really good eyes, you can maybe see that. And so here, the height of this, or the length, if you will, 1/2 positive 3.4 meters per second. And then the width here, it goes from 2 to 3 seconds, right? And so it's a width of 1 second. So half of 1 is 1/2, and half of 3.4 is 1.7. Same thing happens with the units. The seconds cancel, so 1.7 meters. And so here we've got an aircraft, a drone, that fell 6.8 meters, but then, you know, turned on by turning on the propellers from the moment it was dropped, 2 seconds later, it's at a speed of 0, and then it climbs back up, and by the end, it's moving 3.4 meters per second up, but by 3 seconds, it's only sort of made up 1.7 meters of the 6.8 meters that it fell. And so now we need to sort of negative 6.8 plus 1.7. That's how many meters? Negative 5.1 meters. And remember, the negative sign gives us the direction here because they tell us that up is positive. And so we have both the answers here. Well, that would have been sweet if it would have worked out, where I just like slid it down and then the answer was right there. Anyway, you see the working there, and it's easy to sort of do the working on the graph for this. If you think about it sort of more geometrically, right? Those are the areas of those triangles. And then you can transfer your answers here. So we would have the magnitude of displacement, 5.1 meters, and the direction of displacement is down, right? Because the negative sign. So it has a net change in position of 5.1 meters down. Remember that that's what displacement is a change in position. Lily had a question?
Yeah, I have 2 questions. So for magnitude, you not have to like say positive or negative?
The positive and negative is the direction. So they sort of ask us for that here. So the magnitude is just the amount. So think about a vector like displacement. Displacement's a vector, right? So vectors have both magnitude and direction. And so the magnitude is just the how much, right? If you were to say negative or positive, you're really kind of answering this part of it. So the fact that they already ask us to sort of state that, it's redundant to, you know, but I don't think they'd mark it wrong if you put like negative 5.1 here. Okay.
And then visually finding the displacement, why would it be like this triangle minus that triangle instead of just like the area under the triangle?
You mean like the area of like this is the hypotenuse, and we just took the area of all of this space right here. So we're always measuring it relative to the x-axis. Okay, it's like this curve is a triangle right here with the x-axis. And so yeah, that's a really good question. Where are we sort of comparing this? The area sort of what? And so when we're plotting one quantity, velocity against time, it's like this is the length and this is the width. And every area problem, right, is a length times width. It just happens to be a triangle, so we know it's like half of a rectangle, right? So it's 1/2 length times width. And so like this is the dimension that's giving us our width, so to speak. And so we have to sort of calculate relative to that. This is just some sort of arbitrary velocity value down here. So if you were to take the area of this sort of big triangle, you know, you're sort of comparing it to what? To like negative 6.8 meters per second. And so it wouldn't be sort of, it wouldn't give us the correct answer, because remember, how did we derive the equations of motion? It's by considering things like, oh, well, the area underneath this gives displacement. If you think about sort of a more straightforward example, like for example, if we just said, what if something was moving 1 meter per second for 1 second, right? Then the area underneath that would just be length times width. So it's a 1 meter per second times 1 second. That thing went 1 meter, and that would be the area sort of underneath this, right? So we're measuring that sort of relative to like this time dimension. And that's like a length times width, that constant velocity of 1 meter per second. But if we increase like from 0 up to 1, right, then we have a 1/2 base times height. It's like a triangle is half of a rectangle, but it's all an area problem, sort of, you know, this dimension times this dimension here. So always sort of do it relative to the x-axis. All right, what's the change in gravitational potential energy from time t equals 0 to time t equals 3 seconds? Let's remind ourselves that we just calculated 5.1 meters down. So the change in gravitational potential energy, hopefully you've got a potential energy due to gravity or gravitational potential energy is equal to mass times gravity times height. And we kind of think about like the mass and the gravity didn't change. In fact, they told us what that was. Mg is weight. And they told us that there's 15 newtons of weight here. Okay. And so it is kind of hidden within there that you have to connect the idea that Mg is weight, and they give us the weight of the block. And they tell us up here that we are determining for the block, right? For the block, not necessarily the drone, but just for the block. So we know the weight of the block is 15 newtons. Now, what's its change in position? Its height. Well, change in position, that's a displacement, right? We know that we've just calculated what that displacement vector is, 5.1 meters. And it's actually decreasing, right? Like it went a net change down. So its actual change in gravitational potential energy is, a decrease, but they don't really ask us about that. And in fact, energy is a scalar. So we could say, well, it lost gravitational potential energy, but they're really just asking us, like, what is the change? And so we'd have our 15 newtons, our mg 15 newtons, times our height, 5.1 meters. All right, now if you didn't get this here, but you knew to like substitute it in to this equation, that would be an error carried forward. And as you mark this, you want to kind of give yourself those points. So like if this step were correct, but you just, whatever answer you got here, if you didn't give yourself the marks for this because you didn't do this correct, but you knew whatever I got here, I'm supposed to substitute into my gravity equation, then you would get an ECF, error carried forward. We penalize you for this mistake, but we don't continue to penalize you. Okay, it's not fair to keep penalizing you for a mistake when we sort of need that answer in the next one. So 15 newtons times 5.1 meters is a Newton meter, or a joule of energy. Remember, like work is force times distance, and the force to lift something is its weight, and the displacement vertically is height, and so that's where that comes from. And this gives us 76.5, and I'll call it 77 joules. And, you have a negative, energy can be positive or negative, even though it's a scalar. It's just sort of like, is the force in the direction of displacement? It's like you can do positive work. It's like I can do work against gravity, or gravity's doing sort of like the negative work if I lift something up. I'm doing the positive work because I'm exerting the force in the direction of the displacement. But gravity's sort of like doing negative work. Gravity's exerting a force on it, sort of doing the negative work. All right, and then it says calculate the magnitude of the acceleration of the block at time t equals 0. The acceleration is going to be the slope of that velocity time graph, okay? And I kind of recall that it had an initial velocity of negative 6.8 and then a final velocity of positive 3.4, and that happened over a time of, I think, 3 total seconds. So that's one way to calculate it. But is it the easiest way to calculate it? The acceleration at 2 seconds. I think that question is designed to sort of test students' understanding of, do they have a misconception like, oh, because the velocity is 0, it's not accelerating? Well, no, that's not true. It is accelerating. In fact, there's a constant slope all throughout this motion. And so that's a constant acceleration. It has the same acceleration at 2 seconds as it had here or here. We just need to find the slope of this line anywhere. All right, that's sort of the path to the solution. It's a mistake to say, oh, it's going a velocity of 0, therefore no acceleration. All right, so if you said 0, that's incorrect. But maybe that's a nice point to calculate with, because I like calculating with 0 if I can. 0 and 1 are kind of like my favorite numbers to calculate with. Unfortunately, 1, it's hard to read off exactly what that is. No, maybe not. All right, and so let's calculate with like the friendliest numbers possible. Here I have, right, so we're calculating the acceleration of the block at 2 seconds, which is just the slope anywhere, sort of here. And so I'm going to use this coordinate. That coordinate is 2, 0. Again, I like calculating with 0 if I have a choice. It's up to you though. You could have calculated with this. Well, that's a 0 too. All right, this one over here was 3.4. Okay. The other thing that I like is positive numbers. And so it's like, yeah, I could calculate with this 0, but then I get like negative 6.8. No worries if you're comfortable with the negative numbers. Plus, you get a calculator. And remember, yesterday we had a calculator check. All right, so the difference in the y's over the difference in the x's, 3.4 meters per second per 1 second, or 3.4 meters per second squared. We would have got the same thing if we would have considered the point 0, negative 6.8, and like the zeros of the function. So here's like the y-intercept, here's the x-intercept. And so this was 2, 0. We could have done the same thing with these coordinates, or with that one, right? Any 2 points here that are your favorite, all right? But you should get this constant acceleration of 3.4 meters per second. This isn't so bad right here, right? You have 1 in the denominator. So that's the working, kind of pick some points, do a slope. And again, the equations of motion sort of come from this. And so remember that acceleration. Acceleration is the rate of change of velocity. And so equation 1, of our equations of uniformly accelerated motion, it's kind of like this. And so we can just like solve this for A. If you memorize this equation, you could rewrite it and it would become this. You should memorize this too. That's sort of the definition of acceleration. So just take, the final velocity, 3.4, minus the initial velocity, negative 6.8 over 3 seconds. And then you'd get, the same 3.4 meters per second squared. Right, so we had the final velocity was 3.4 minus the initial velocity, negative 6.8 over the 3 seconds of motion. And so this is yet another way to, sort of think about it. And it should agree with the conclusion we just reached by calculating the slope from like 2 to 3 seconds. Remember, we got 3.4. So 3.4 plus 6.8 divided by 3 is also 3.4 meters per second. So it's always going to work, okay? Just find some good points there and plug them in. Now use your answer here. And if it ever tells you to do something, do it. Follow the directions. So we need to use this answer to show that the tension in the wire at 2 seconds is 20 newtons. Okay. So this seems like a Newton's second law type of problem. And Newton's second law is sort of usually always the one that it is, right? That's a very typical way to begin, physics calculations. Think about Newton's second law. So tension is a force, but there's also the weight force, okay? And so it's kind of like when this thing wasn't moving, Newton's first law, there was no force, there was no acceleration. It had 15 newtons of weight, so it has to provide that force. The tension in the wire has to provide the 15 newtons of weight, even if it's not moving, even if it's not accelerating. But it is accelerating at 3.4 meters per second squared. And so mass times acceleration is always the sum of the forces. The resultant force is always mass times acceleration. Let's just sort of calculate what we can right now. What is the mass of the block? We may not know the mass of the block, but we know the weight of the block is 15 newtons. And we know that weight is equal to mg. And we know that on Earth, G is 9.81. Let's use newtons per kilogram. Remember, a newton per kilogram is the same thing as a meter per second squared. So like the acceleration due to gravity or the force per unit mass, 2 equivalent ways to think about the strength of Earth's gravity field. I like newtons per kilogram here because then it's easier to see like, okay, yeah, newtons cancels and I'm left with kilograms. So if I divide each side by Earth's gravitational field strength, 9.81 newtons per kilogram, newtons cancels, I'm left with kilograms of mass. Got to do it to both sides of the equation. And then, so what is the mass of my block? 15 divided by 9.81 gives me a mass of 1.53. So that's the mass that I'm accelerating. My block is 1.53 kilograms of matter, right? Mass is the amount of matter. And I've calculated the acceleration to be 3.4 meters per second squared. So that's what the net force is. It's that product. All right. 1.52 times 3.4 equals. All right, so the net force that causes this acceleration is 5.168 newtons. Okay, now we need to show that the tension in the wire is 20 newtons. So the tension has to provide all of the force for the weight of the thing, the 15 newtons, plus it's the thing providing the net force that causes it to accelerate, right? And so the tension is providing both the force supporting the weight and the extra force that causes the acceleration. And so we could say that tension is equal to the weight plus, how do we call this? The resultant force. And so the weight was 15 newtons. The resultant was 5.1, 5.2 newtons. And that is indeed about 20 newtons. So it checks out. All right. The tension is providing both the force required to match the weight plus the resultant force causing it to accelerate. All right, if you need any of that working for a moment or two longer, pause the video because it's going to be gone. If you're in class, you're like, I can't pause the video, but like you will be able to later. All right, just check it out on YouTube. The wire has a cross-sectional area of 2.8 by 10 to the -5 meters square and is made from metal of Young modulus 1.7 by 10 to the 11 pascals. The wire obeys Hooke's law. Calculate the strain of the wire at time 2 seconds. And so you see how it's like, wow, this thing brought us all the way through Newton's laws. We're talking about displacement. It's chapter 1. We did some acceleration, velocity, time graphs, and now we're into chapter 7. And this is the same question. So this is kind of a favorite of ACE physics where they like to combine many different ideas into the same question. And it's somewhat of a real world problem, like a drone that, lifting a weight. I think there's actually a lot of companies that are moving towards this to do their deliveries. Like Amazon will just sort of fly a drone to your house, so it'd be like, okay, drop this drone out of the window, turn the propellers on because it's going to drop 5.1 meters, before it can pick back up or whatever. That's going to be the future. It's already here. We're living in tomorrow, today. All right, let's start with Young modulus. It's stress over strain. Here, the force over area over extension over length, or FL over AX, is not going to be the way we want to go with it, right? Because we're solving for the strain, right? We're solving for this. They give us the Young modulus, and we have to calculate the stress, right? They're not friendly enough to be like, here's the stress, here's the Young modulus, what's the strain? That's like, okay, at least you got to calculate one of them, right? We'll give you the Young modulus. We'll even give it to you in friendly units, pascals, so no conversion necessary, no gigapascals. They could have said 170 gigapascals. That's the same thing, right? Then we'd have to convert gigapascals to pascals. So think about like all the levels of complexity that go into a calculation. You need to size it up and go, oh, a conversion here. Hey, nice, no conversions for this one. They gave us a cross-sectional area in meters squared. What else could they have done? They could have given us the diameter of the wire. And then we would have to calculate the radius. We'd have to know pi r squared is the cross-section of a cylinder. And then we'd have to calculate this ourselves. So those are the sort of other types of ways that this information is presented. In my mind, I want to make epsilon, the strain here, the subject. And so I'd rewrite this as epsilon equal to stress over Young modulus. And then the stress, you may recall, is force per area. So that's going to be over the Young modulus. The force, okay, At time 2 seconds, do we know the force on the wire? I heard somebody say, that's the 20 newtons we just solved for a moment ago. We show, and even if we didn't know that, it's given, right? They say, show that the tension is 20 newtons. So even if you're like, I can't show that it is, but I trust that the question isn't lying to me. So you plug in that value for force. Okay, 20 newtons. The area, again, was just kind of given. Nice. 2.8 by 10 to the negative 5 meters squared. Remember, a Newton per meter squared is indeed a Pascal. Strain is dimensionless. That's why there's no units over here. And so when we divide the stress, the pascals of stress by the Young modulus, 1.7 by 10 to the 11 newtons per meter squared, right? That's what a Pascal is. Then we kind of see, okay, newtons per meter squared, those are going to cancel. And now we just have to push these buttons correctly in our calculator, which seems like, well, that should maybe be the easy part, but it's easy to make a mistake there too. So listen as I sort of talk through this button pushing. 20 divided by, open parentheses, 2.8 times 10 raised to the negative 5, close parentheses, equals. So now I've calculated the stress. It's 714,285. But I don't really need to know that. I want to take that stress and divide it by the Young modulus. And so divided by, open parentheses, 1.7 times 10 raised to the 11, close parentheses, right? Use grouping symbols when you're dividing by values in scientific notation. Because your calculator will rigidly follow the order of operations, and it will divide by this, and then it will multiply by 100 billion. But you want to divide by 170 billion, right? You want to divide by this big number, not divide by a small number and then multiply by a big one. You're trying to divide by a big number. So give the calculator the language it understands. It knows to evaluate everything in the grouping symbols, the parentheses first, right? Because that is the order of operation. So when I hit equals, my calculator tells me the strain is 4.2 by 10 to the negative 1, 2, 3, 4, 5, 6. All right, and no units. Remember that strain is dimensionless. Let's just remind ourselves that strain is the ratio of the extension to the original length. And so that force is causing the wire to stretch out a little bit. If we compare that stretching out to its original length, it's this. Right, that's the ratio of how much it's stretched out compared to its original length. Hardly at all, right? Very small. At some time after t equals 3 seconds, the tension in the wire has a constant value of 15. State and explain whether it is possible to deduce that the block is moving vertically after t equals 3 seconds. And so that's sort of beyond where we're given data, but they do tell us that there's a constant value of 15 newtons in that wire. Does anybody know whether or not we can deduce whether it's moving vertically? You said you don't think so? You can't, okay? If you connect it back to the very first idea of Newton's first law, it says objects move at constant velocity unless the resultant force acts. And so the fact that they tell us that the tension is back to the weight, right? It's back to the weight of the block. Well, now there's no net force, and no net force means no acceleration, but we can't deduce whether it's moving or not. It could be moving with constant velocity. It could be at rest, right? That's all we could deduce. We could say, well, there's no net force, but we can't really deduce whether it's moving. It could be sitting stationary, you know, at where it's delivered that package, or it could be just flying along at constant velocity. Okay, moving at constant velocity. It wasn't moving at constant velocity when it had that 20 Newton force, right? Because we had the 50 newtons plus the 5, right? It was accelerating that. It was trying to pick up velocity in the vertical direction, right? Trying to fly back up. But sometime later, it's like, okay, I've made up the 5.1 meters I dropped. Now I'm flying along at level, or maybe it goes a little bit higher than that, right? So it's like you drop a drone out of a window and say, you know, fly bird, go deliver this package. You know, and it falls down, the propellers kick on, it picks back up, right? And it gets to some elevation that it's safe to fly at. And now it doesn't need to accelerate anymore in the up direction. It can just fly along with a constant velocity in the vertical direction, or it might be at rest, but we cannot deduce whether or not it's moving. Okay, so the answer is the object could be at rest or it could be moving with constant velocity, and therefore we cannot deduce whether it's moving vertically after t equals 3 seconds. And you can kind of put that into your own words. 2 marks for that. Trash that. All right, a blank page. And then the rest of the quiz. State what is meant by the mass of a body. The mass of a body is the amount of matter it possesses. Okay, mass is the amount of matter. We measure mass in kilograms. Okay, and then remember that mass is inertia, the tendency to resist change in motion. So all those are good ways to think about mass. 2 blocks travel directly towards each other along a horizontal frictionless surface. The blocks collide as illustrated in figure 3.1. Block A has a mass 3m, block B has a mass m. Before the collision, block A moves to the right with a speed of 0.4 meters per second, and block B moves to the left with a speed of 0.25 meters per second. After the collision, block A moves to the right with a speed of 0.2 meters per second, and block B moves to the right with a speed b. Use Newton's third law to explain why, during the collision, the change in momentum of block A is equal and opposite to the change in momentum of block B. The key ideas here are that Newton's third law, first of all, states forces exist in pairs, equal in magnitude, opposite in direction, okay, between 2 objects. So those forces exist in pairs between 2 objects, and they're equal in magnitude and opposite in direction. And so we say Newton's third law tells us that the force is the same. The force exerted by this block A is the same as the force exerted from block B on block A. The force of block A on B is the same as block B on A. They're just opposite. They're equal and opposite. The change in momentum, now force is the rate of change of momentum. So we say Newton's third law tells us the forces are equal. Newton's second law says force is the rate of change of momentum. Okay, so we have force being equal to the rate of change of momentum. The question is really asking us, how can we use Newton's third law, which says the forces between these guys are the same, to explain why during the collision, this quantity, the change in momentum of block A, is equal and opposite to the change in momentum of block B. Well, if the forces are the same and the time of collision is the same, that's kind of what it means to collide, right? Like the 2 objects are touching each other for the same amount of time, right? As soon as they separate, they're no longer, you know, in contact with each other. And so Newton's third law says is that the forces are the same, equal and opposite, and they collide for the same time, and therefore the change in momentum must be equal and opposite. Okay, so kind of use Newton's third law to explain how the forces are the same, and then the objects are in contact for the same amount of time, and therefore the change in momentum must be the same. All right, and I leave it to you to kind of put that into your own words, and we'll take a look at the mark scheme once we're sort of done with all of this, and we'll look at the language that they say is, you know, appropriate, and we can use that to further score our quiz here. The next one says determine the speed v. All right, and so that's the speed of this second object, block B. Let's see if I can. All right, so we have obviously the law of conservation of momentum is here. Just look at the language before the collision, after the collision. So it should, like, even just looking at the figure, you should kind of see like, oh, this is a momentum type problem, right? I'm going to use the law of conservation of momentum here. So let's remind ourselves what that is. That says that the initial momentum of all the objects before the collision is equal to the final momentum of all the objects after the collision. So we'll calculate the initial first. We've got object block A, which is 3m, that's its mass, times its velocity 0.4 meters per second. So that would be its momentum. Remember, the sum of all the momenta of the objects is the initial momentum. And so the momentum of object block B would be m times its speed, or its velocity, which is negative 0.25 meters per second. Take care of the opposition of these velocity vectors. That one has to oppose the other one. So I'm calling right positive, and so this velocity is negative. The final momentum is going to be 3m moving at speed 0.2 meters per second plus m moving at speed v. Okay. So I'm just kind of looking at this figure up here going, that's my left side of the equation. This is my right side of the equation. There's my one unknown. They give me not the mass in kilograms, but like just in terms of m. And so hopefully, I mean, if you can't see already, that won't be a problem. Then just kind of trust that, hey, once I do my algebra, that'll hopefully work. I do not have two unknowns here. Otherwise, it would be impossible. I would need another equation to solve it. All right, now let me scroll down a bit. Oh, that's not good. So yeah, that stays there. Forget that then. Let's calculate. All right, 3 times 0.4, what's that, 1.2? So we have 1.2 m plus negative 0.25 m equals 3m times 0.2 meters per second is 0.6 m plus mv. All right. 1.2 m plus negative 0.25 m is how many m? 0.95 m equals 0.6 m plus mv. All right, so that's the next step here. Just combine these like terms, right? I drew it over here because I ran out of space. Next, subtract 0.6 m from both sides. Gets rid of it over there. So 0.95 m minus 0.6 m gives me 0.35 m equals mv. Divide each side by m, right? Because I'm solving for v, and that gets rid of that. Okay, and so v is just 0.35 meters per second. Now, really, like when I multiplied this 3m by 0.4 meters per second, it was really 1.2 m meters per second, right? Like that was still there, but that looks really kind of cluttered. Okay, so I just kind of dropped the units, knowing that when I solve for v, everything is in the right units. Like there's no centimeters per second, kilometers per hour, light years per decade. There's no other kind of oddball unit. And so we've deduced that the velocity is 0.35 meters per second. V equals 0.35. Good. If you need any of this working for a moment or two longer, pause the video because it's gone. It's like, no, I needed that. Calculate for the blocks the relative speed of approach, the relative speed of separation. Okay, so let's go back up here and do that. Oh no, I completely forgot what this was. Now I got to start over. Why was I so quick to erase it? All right, in searching my memory banks, I found the value of 0.35 meters per second. What is the relative speed of approach here? You're saying, well, these are going in opposite directions, so I'm going to add them because two objects that are traveling sort of towards each other see each other moving at the sum of the speeds, right? The relative speed of approach, when two objects move in the opposite direction, we add. And so 0.4 plus 0.25 is 0.65 meters per second. That is the relative speed of approach. How about the relative speed of separation? So these things collide and then they both move this way. And so now they're going in the same direction, same subtract. right? So how fast do they see each other? This one doesn't see it speeding away at 0.35 because it's catching up to it, 0.2 meters every second. And so it only sees it going away at what? The difference, right? So same subtract. And so 0.35 minus 0.2 is 0.15 meters per second. And that's the relative speed of separation. And you probably recall in our studies of momentum that if these are equal, then it's a perfectly elastic collision. Like, why would they have us calculate this unless they wanted us to state next, hey, is this collision elastic or not? It's kind of an easy way to check it. Okay, just like, okay, if those are the same, then it's perfectly elastic. If not, it's inelastic, which most collisions are. And here it's very clear that they're not the same, right? 0.65 is not equal to 0.15. Oh man, I should have done that so that fit, like, you know, in these boxes. Anyway, relative speed of approach 0.65, relative speed of separation 0.15. That one kind of works there. Maybe I could use my erasing tool. Is this an eraser here? So we'll go. This guy. And all that redundant. It already says it right there. .65 meters per second. Relative speed of separation, 0.15 meters per second. And again, kind of just recall, as we're using this as a chance not just to sort of score our quiz, but to review that the relative speed of something traveling in the opposite direction, we add their relative speeds to calculate the relative speed. And so because they were going in opposite directions, it was 0.4 plus 0.25, okay, because opposite direction. The relative speed of separation, we subtracted the value, so it was 0.35 minus 0.2 to give us this because they were going in the same direction. So same subtract to calculate relative speed, opposite add to calculate relative speed. And if the relative speed of approach does not equal the relative speed of separation, the collision is inelastic. Inelastic because the relative speed of approach does not equal the relative speed of separation. All right, if you add all that up, that's out of 24 marks.